All right, in the previous lecture, we learned that streamlines are a pretty good way to visualize what's happening in a flow. Because basically they represent the trajectory of a particle, at least for steady state flow. Even though streamlines, path lines, and streak lines are different things, for steady state flow, they turn out to be the same things. And so they're a good way of describing flow patterns. And it turns out that they're easier to mathematically work with than some of the other ones. So let me show you a couple of different common flow patterns where you can actually calculate the streamlines exactly by hand. Okay, so our definition of a streamline is that locally the slope of a streamline should be parallel or like tangent to the local velocity vector. So in math, what that means is that the slope dy dx is, you can think about that as the rise over the run, should be equal to the rise in the velocity vector over the x component of the velocity vector. Or equivalently, for a given, so I can sort of move that over in a different way and write that the length dx of a piece of the streamline should, move proportionally to the horizontal component of velocity, while the vertical component, its length, scales with the vertical component of velocity. And when you write it that way, it's actually pretty easy to extend it to 3 dimensions and realize that if I was in 3 dimensions, there's also a z length to each length of the streamline that moves proportionally to the so-called the z component of velocity, which would be called w. You can also extend that to polar coordinates, right? So in polar coordinates, you'd be given, say, the radial velocity and the tangential velocity that I'll call v sub theta. In that case, the radial length of a component of the streamline should move in lockstep with the radial velocity, while the tangential length, which would be like r d theta for an element, that has like a length component in the theta direction. So r d theta divided by, should move in lockstep with the tangential velocity. Let's do an example problem. So I'll write an example velocity field. So suppose that this velocity field is known, right? So let's suppose that our Eulerian description, which means that we know like how the velocity depends on the spatial location. Suppose that that's a given, right? So in this case, u equals minus k times y, so that's the horizontal component, and the vertical component is k times x, where k is some constant that, for the sake of argument, let's say that's a positive constant. So then all we really need to do to figure out what the streamline is sort of follow our prescription here. So we'll just plug in dx over u, so u is minus ky, equals dy divided by kx, where, where that's the vertical velocity component. So the k's in that case cancel. And before I do any more work, let's think carefully about what our objective here is. So we're looking to find the equation of a streamline. What does that mean? It means that I'm looking for the equation that describes the shape of the curve of the streamline. So y versus x, right? So to make a plot, I need the equation of some line y versus x. In fact, sometimes it won't be an explicit equation like that. It'll be what's called an implicit equation for y versus x. But generally, I'm looking to figure out a line or a curve and that describes how the y coordinate of the curve depends on the x coordinate of the curve. So what I need to do is solve that differential equation. So in this case, the k's cancel here, and I can write that I can move the x and the y over to the respective sides of the equation. So x dx equals minus y dy. And then what I need to do is integrate both sides of that equation. There are different ways you can do that. So you can, integrate and do an indefinite integral, in which case integrating either side of that equation is going to give you like an integration constant that I'll get one on both sides of the equation, but I could combine it into one integration constant. But I'll argue that a better way to do this is to actually do definite integration from some specific point x0 and y0. And you'll see why that's useful in a second. So what I'm going to do is take the integral of both sides. So I'm going to integrate x from x0 to some arbitrary point on the streamline x, and I'll integrate over y from y0 to some point on the streamline y. So in this case, that's pretty easy to do. So that'll give you half times x squared minus x0 squared. And then the right-hand side will give you half times y squared minus y0 squared. And I can separate those. So like I just solve algebraically, and I can see that I can separate that in a convenient form where I can interpret what that geometry is. So one way to do this is to move it over so that it's x squared plus y squared equals x0 squared plus y0 squared. Okay, so what does that mean? Well, x squared plus y squared equals a constant would be the equation of a circle. But this isn't just any circle. It's a circle that passes through the point x0, y0, because of how I chose to do the integration. So what I can do is I can plot the streamlines. I can go like plot x versus y, and I see that it traces out a family of circles. And which circle it creates depends on what the initial value was, like the x0 and the y0. So like here I've shown like 3 different starting points depending on where x0 and y0 were. So, so in this case, here's 3 different streamlines of the flow that depend on the initial condition. So now we need to answer the question, which way does the fluid flow in this diagram? So I have a streamline. I sort of know what the pattern looked like. However this fluid is flowing, it's flowing around in circles. But which direction does it flow? To do that, the easiest way is to just look at the velocities that are given, so the u and the v. So if I look up top, v, the vertical component of velocity, depends on stuff, right? So in this case, it's given by k times x. That means that for a positive value of x, the vertical component of the velocity, so like the up and down motion, is positive, meaning upwards. So that means that everywhere in the right 2 quadrants of this graph, the flow is going upwards, and everywhere on the left side, so like x negative, v would be a negative number, so that means that the flow would be going downwards. So that's how you assign the arrows that go in these things. You actually evaluate the velocity at a couple of particular points that help you figure out what that is. Alternatively, what you can do is solve that same problem in cylindrical coordinates. So if you were doing this in cylindrical coordinates, then instead of receiving the velocity field written in terms of u and v, you'd receive it in the form vr and v theta. So as it turns out, the flow that I just showed you is actually rigid body rotation. It's not a very interesting flow pattern at all. You could write that as v sub r equals 0 and v sub theta equals some constant times the radius, or how far away you are. So if we follow our usual prescription, we can write that dr, the radial length divided by the radial velocity, is equal to the tangential length divided by the tangential velocity. So rd theta divided by v sub theta. And then plug in. Because v sub r is 0, you don't want to divide by 0, so it's best to multiply both sides of that by their denominators. But then in that case, you can see that since v sub r is 0, one side goes away, and you're left with the fact that r is a constant, which is exactly what we found, right? We found a family of circles when we solved for the streamlines in Cartesian. If you do the same thing in cylindrical coordinates, you'll also find a family of circles. You'll just find it more easily.